So let's get started today. So two things on the agenda today. First of all, I heard that many of you had difficulty with the recursion in Lab 9. So I wanted to go over, especially on Shapeshifter, so I wanted to go over kind of the general outlines of that solution, so to give you an idea of how it could have been done. And then the second thing is we're going to be going into AVL trees. And because of Shapeshifter, depending on how long it takes, we may not completely get through AVL trees today and may have to finish them on Thursday. And your lab covers AVL trees, but I don't think it's a big deal because you'll still have plenty of time to get AVL trees done. Also, even if we don't get completely through AVL trees, we'll get through enough that you can get started on the lab tomorrow if you want to. Okay, so the Shapeshifter part, that was the one that the TAs communicated most of you had the most trouble with, is that you have this idea that things are either shields or swords, and you're applying these shapes to this grid, and the idea is that eventually you want to turn all of the shields into swords. So you're being presented with shapes in a specific order. So in this case, you're going to be first presented with this horizontal shape, then this Tetris-looking shape, and then this shape. So they'll come in order, 1, 2, 3. And you have to apply each shape once and in the order that it was presented to you. And you can apply it anywhere on the grid where it would fit. So, for example, this first shape, there's exactly 3 places on the grid it could fit. Here is 1, here is 2, and here's 3. It can't fit anywhere else because let's say you tried to instead fit it starting here. The first 2 elements would fit, but the third one would fall outside the grid. So you can't apply shape 1 to any column other than to column 0. Now for the next shape, you can apply, so this is our next shape, so you can apply it here. Okay. Where else could you apply it? That's one place. Can I apply it here? No, why not?
The second row, the third one will open.
Very good. So I could apply the first row here, but then this row would have to go here and there, and it's no good. Okay? So, where is another place that shape 2 can be applied?
One block under shape 1.
Very good. So 1 block under. So the second place is right there. And those are the only 2 places it can be applied. Because if you try to apply it in row 3, what happens?
It's going to go outside.
It's going to go outside on the bottom. And if you try to apply it in column 2, it will, this last piece will always end up outside, right? And then the last shape, there's 3 places it can be applied. What are the 3 places? So the last shape is...
First column, second column.
Exactly. So the last shape is this one. It can be applied in the first column, the second column, or the third column. Okay? So, again, the first thing is to make sure everyone understands it. I think most of you understood it, but just to make sure, is it flips whatever the sword and shield are. So, for example, if I apply this shape right here, the horizontal one, to the first row, it will flip this sword to be a shield. So it goes from this row to to this row. And you can see it flipped the swords and shields. So the swords became shields and the shields became swords. So we're just flipping them. And let's see, then we're applying this shape right here. Gets applied to row 2. So this, and this. You're going to see that down here, this became a shield. These 3 became swords. Okay, so the idea is if you apply them in the right place, so finally this shape, if you apply it to to column 0, it becomes all swords. So that's an example of a puzzle that can be solved. Now, Dr. Planck in the lab is saying, okay, we want to solve this using a computer because sometimes we get pissed off trying to solve it as a human, especially the more complicated ones. And we need to do it in a systematic way. So the first thing we need to do is kind of figure out data structures. So it makes sense to organize a grid probably using some kind of array or vector. And because we're just dealing with 2 types of elements, swords and shields, we can pretty much use bits to represent swords and I'm just going to do this all period, which is I'm going to have trouble with swords and shields. I just know it. Okay, so when I was a kid, I had difficulty learning English. In 1st and 2nd grades, I actually had to go to some language training, and I still have trouble when I have to put things like similar sounding consonants together. That's why you're going to hear me bobble on swords and shields occasionally. Okay, so just bear with me when I do that. So we're going to represent one of them as a 1 and the other as a 0. It doesn't really matter which way you go, although I think he may have decided for you which way to go. In fact, he did. So he's going to say shields are 0s and swords are 1s. And he's going to give them the grids to you as strings, with each string representing 1 row. So this first string, 1, 0, 0, says that we have a sword followed by 2 shields. And he's guaranteeing that I'm not sure he's guaranteeing, but each string is supposed to have the same length. So he's not guaranteeing that there will be an equal number of rows and columns, but he is guaranteeing that the rows will all have the same width or same number of columns. And then he's also coming up with a representation for his shapes. So a shape is also represented with each row represents each string represents a row. So this was the shape that was 3 in a line. The second one, because there's 2 strings, you know there's 2 rows. So the first row is colored in. And then the second row, this one, first one is blank, and the next 2 are colored in. Okay? And then the third row, you'll notice that if the remaining elements are 0s, he doesn't include the 0s. So you can assume that as soon as the string ends, the remaining elements in the column are 0s. So the fact that it's 1, 1, 1 indicates that the first column is a 1 and everything else is a 0. Second one, the same thing. Third one, the same thing. So that's why you know it's a vertical stripe like that. Okay, so that's setting up simply the data structures. Okay, the big thing is figuring out how to do apply these shapes systematically. So we know each shape will be applied once in the order that it is presented. So that means in this first case, this is shape 1, this is shape 2, and this is shape 3, and they have to be applied in that order. Okay? And the best way to tackle this problem was the same way we tackled the Sudoku problem. Okay, if you remember with Sudoku, we had this grid, okay, and some of the numbers were filled in for us. But we started at row 0, column 0, and we just proceeded along row 0 until we exhausted it. Then we came down to row 1, then we came down to row 2, etc. And it turned out that Shapeshifter could be tackled in exactly the same way that you tackled Sudoku. So the idea is that you start with your grid. So let's say that we initially have the grid. Whoops. Let's take a look. So our grid is 1, 0, 0, whoops, 1, 0, 0, 1, 0, 1, 0, 0, 0. So this is our initial grid. Okay, and our initial shape is 1, 1, 1. So we're not going to try to a priori figure out which are the places. Before I just had you eyeball it and tell me where it could be applied. Now we're going to do a systematic search of where it can be applied. So the first thing we're going to do is we're going to start at row 0, column 0, and ask if it can be applied there. Okay? And the answer is yes, it can be applied there. So we're going to try to apply it there. So we're going to apply it by, we flip the bits. Okay, so 1s become 0s, and 0s become 1s. So tentatively, we set it to be like this. And he talks about an operation called bitwise exclusive OR, which you should have been introduced to in 160, at least the idea of exclusive OR. So if you apply exclusive OR, so if we have 1, 0, 0, and we apply 1, 1, 1 to it, exclusive OR essentially flips bits. So 1 and 1 becomes 0, 0 and 1, 1, 0 and 1, 1. So you can use exclusive OR to flip the bits. Not only can you use exclusive OR to flip the bits, so this is the exclusive, this is bitwise exclusive OR. Okay, so it's written something like A caret. It's the caret symbol that's over the 6 on your screen, on your keyboards. So A caret B. So first property of exclusive OR. So nice properties of exclusive OR. And it's often written XOR like that, so you should get used to seeing it written that way, exclusive OR. Okay, the first application of XOR flips bits. And the second application returns the bits to their original, second application with the same mass. So we often talk about when we apply, when we have A exclusive OR B, we typically call B the so-called mask. And it's just jargon, okay? It is a template that we're using to apply to bits. So for example, when we draw pictures on a screen, and we like a bitmap. The bitmap is the mask. It goes on, and typically it's not XOR. It's actually being applied opaquely to the screen. But that element is often called a mask in computer science. So the first application of a mask flips the bits, and the second application with the same mask returns the bits to their original states. That is, if you write A exclusive OR B exclusive OR B, that actually equals A. Okay, it's commutative. It makes sense because if you know exclusive OR, 0 exclusive OR 0 is equal to 0, and 1 exclusive OR 1 is equal to 1, right? Hopefully you learned that. So exclusive OR is commutative. So if you do A exclusive OR B exclusive OR B, that can be grouped as B exclusive OR B, which is going to be 0 no matter what. Right? Because 0 exclusive OR 0 is 0, and 1 exclusive OR 1, I'm sorry, is 0. That was wrong. So no matter what, B exclusive OR B is 0, so you're getting A exclusive OR 0 is equal to A. So two applications of exclusive OR will flip the bits back to their original state. Okay, and that's nice because if we fail with our shape application, we can backtrack by simply XORing it a second time, and it will return it to its original state. So if we have to backtrack, we can simply apply the shape a second time, and it will return the grid to its original shape. So that's very handy. Okay, so once we've applied the first shape, which was 1, 1, 1, we now advance to the second shape, which was 1, 1, 0, 0, 1, 1. Okay, and again, we're going to start at the upper left-hand corner for it. And we will try to apply it. So if we try to apply it, figure out, someone tell me what the bits will be in the grid. Which bits get flipped? Mac, give it a try. So if I'm applying this pattern, starting at this one.
It would be the first or the 0 column.
Okay.
First and second.
Very good. So we're going to flip this one and this one. So they're going to become now 1 and 0.
And then the middle one and the one to the right.
Very good. Those two. So these two also flip. If only I'd remember it's 1, 0, 1, so it's going to become like that. Okay, so now we go to our third shape. And again, we start at column 0, 0. And when we apply it, we get 0, 0, 1. And is that a successful solution? Based on what we said, it has to be all sorts. Is that successful, Jaja? No, because there's a whole bunch of shields left. So that means we have to backtrack. Okay, so the first place we're going to backtrack is going to be on shape 3, because that was the most recent shape we applied. So the first thing we're going to do is we're going to XOR this mask back onto here. So we'll end up with 1. this will go to back to a 1. And this will go to a 0. So this just restores the original state. And now what we're doing is a systematic traversal of the grid. So if we're doing this just like we did in Sudoku, which should be the next square that we apply the pattern to? If we're doing it just like we did when we did Sudoku. Rebecca, I'll ask you this question. Okay, not sure. Man in red behind you. What's your name? Michael. If we're doing it like we did in Sudoku, where should we apply pattern 3 next? So in Sudoku, what did we do? If we failed, well, we went, I guess with Sudoku, we filled in a value, and then which square did we go to next? Right, so what we're going to do is systematically applying it. We tried to apply shape 3 here and it failed, so now we're going to go to this square. And we're going to try to apply it here, which is going to be this column. So we will apply it, and that will give us 1, 1 and 1 is 0, 1 and 0 is 1, but that's still no good, right? So we're going to backtrack to get, let's see, this is 1, 0, 1, so 0, 1, 0. So where's the next place that we apply this pattern 3, based on what I said? To the third one, right here. Okay, and again we apply it, but you can see that since there's zeros in columns 1 and 2, we're just toast, no matter what we do. Okay, now we can try to apply it, now that we failed in row 1, based on what we did in Sudoku, what did we do next? We went to row 2, but we can't apply it in row 2. Why not? Because it would come down and it requires a row 4, which we don't have. Stone.
Before you apply it to column 2 or column 3, don't you have to retroactively apply it back to column 1 to get it back to the original?
Yes, and I was. I guess maybe I was doing it too fast, but I was exclusive ORing it back. So basically, my approach was this one. It was kind of like, I'll call it SSSolver for Shapeshifter solver. And I'm basically saying, let's see, I have a set of shapes, and I have an index into those shapes. And I have my grid. Okay, so what I'm going to do is I'm going to apply shapes of index to systematically to each square in the grid. And then I'm going to call, so each time I apply it, for each application, I will call SSSolver shapes index plus 1 because I want it to apply it to the next shape, right? We apply the shapes in order. So, no, I'm not playing grid too well. So for each application up here, I'm calling SSSolver, and if SSSolver ever succeeds, I return true, because that means I found a solution. and otherwise, if I ever if I ever get down to the bottom, I return false to indicate that I failed. Now, the lab had you printing out some information if you succeeded, but all we're worried about is trying to find a solution. So if it succeeded, you were printing out the shape and which row and column it was applied to, but we're just returning true for the time being. So the next thing we have to do is to figure out how to apply the shape systematically to each square in the grid. Okay, well, we already know that we should be starting at, so notice again how I'm starting with pseudocode, and then I'm slowly filling it in with more and more details, which I think is a good way to develop a program. So I know that I'm starting at row 0. So I'm basically going to say for row equals 0, what's the biggest row that I can consider applying a shape to? If I have n rows, let's say that there's n rows in the grid, can I always apply a shape to the last row? Let's go back here. Okay. Was I able to apply this shape right here to the last row? No, why not?
Because it would have gone off the grid.
Right. So I'm going to, so basically, I know that it's no good to go in all cases up to the last row. I need to go to n rows minus what?
The size of
Right. Well, let's call it the height. Okay, so let's say the height of shape. And again, you'd have to figure this out. It's not my goal here to give you the whole solution. I'm going to make index be I so that I don't have to write everything out so much. You'd have to figure out some of how to do this, but okay, basically for row equals 0 to n rows minus height because of the shape, whatever it might be. Okay, and we're going to systematically start at column equals 0. And again, we're going to go to how high can we go?
the width of the shape.
The width. So to the number of columns minus the width of the shape. Okay, so that's a systematic application of the shape to every single square of the grid that will allow it. Okay, basically, we are not going, whenever we know it would either slop below the bottom of the grid or to the right of the grid, we stop. Okay, and the application is going to be using that exclusive OR operation. So again, I'm not going to, you're going to have to be able to figure that out yourself, but it's going to be starting with you're going to start at grid, row, column, and you're going to basically exclusive OR it with shapes I. Now you're going to have to write a couple for loops to actually do that, but that's the idea, is you're starting at this particular square, you're exclusive ORing it with shapes. Then we would call SSSolver. So we can say if SSSolver, okay, return true. And then in answer to what Stone said earlier, if it fails, we have to set it back. So if it failed, else we return the grid to its original state. And we'll move on to the next grid square. And there in pseudocode is what your Shapeshifter solver should have looked like. So it's systematically for a certain shape. It is almost, I have to add one thing to it. So it's systematically applying that shape I to each valid grid portion of the grid, then asking if it can be solved for shapes, and I'll say I plus 1 to make it consistent with what I had. Okay, and then we move on to the next shape and we make a recursive call. Okay, if we fail, then right here we revert the grid back to what it was and advance to the next grid cell to try. If we succeed it, we return true. Now in your real thing you would have printed out some information about the shape in which row and column you were applying it at, so someone could actually recreate your solution. What's the one thing I'm missing from here? What does I have the recursive case, but what is the second thing that every recursion requires? The base case. And I have not given you the base case here. What is the base case? At what point would I not want to continue? Or where I could just return true?
All the rows and columns are one. Pretty much when everything agrees one.
That's right. So it would be if all the rows and columns are all ones, and what's the second requirement? It's not good enough. You can't have, it could be that, yeah, keep going.
No, you can't have any shapes remaining.
You can't have any shapes remaining. So there's a condition before, so I'm missing a base case here. Okay, and that base case is if, say, I is greater than or equal to shapes.size, and grid is, I think swords are 1, right? Okay, and grid is all ones. Again, you'd have to write a test for that. Return true. So you check the grid. Once you've exhausted the shapes, you check the grid. If the grid is all ones, you return true, and otherwise you return what? What's the opposite of true? False. Okay, so else, because if it's not all ones, then we didn't solve it, so it must be false. So that's our base case. Okay, and that actually goes up at the very top. Okay, so if we've exhausted the shapes and the grid is all ones, we return true, else we return false. So that's your solution to, now I know there was a bit more code in all this, but this is your basic solution. Yes, Jojo?
When I apply the fold to apply the shape on the grid, my fold is the size minus height and plus 1.
Okay, let's see.
Anyway,
So you would start at, okay, so how did you,
I put row equal to 0 and row size minus the row for the shape.
okay, so if you have to be careful because you're already using row and column here, so you might want to say shape, you probably want to say something like for shape row. Otherwise, if I reuse row, I'm going to get toasted.
Oh, I use I.
Okay. I'm going to say shape row.
Okay.
So you said shape row equals 0, presumably to number of shape rows. And you'd write a second one for shape columns. equals 0 to number of shape columns. Okay, is this making sense? Then I'm going to have to erase something.
I don't really know what you're doing.
You don't know what I'm doing? Okay. Well, okay, how did you apply it?
So I was applying the shape into the row. So
Okay.
my for loop is int I equal to 0 and I is smaller than row size minus the row of the shape.
Okay,
and
just a
plus
second.
1.
Let's, okay, so for I equals 0 to what?
I is smaller than the row size.
Okay. So the shape size, it's the shape, it's,
Great size.
Great.
but it's not the grid size because it should only be the size of the shape. The shape is not necessarily as big as the grid. You can only, so in this application,
Oh, I
it
have-
should only be the number, the width of the shape.
Yeah, it's the row size minus the shape of the shape size.
But it shouldn't be that either. It should be for I equals 0 to shape width, where width is the number of columns in the shape. If the shape has 3, so if you're at, okay, so let's say this is your grid, okay, and you're at this point right here. So row is equal to 0, column is equal to 1. Okay? So, I'm sorry, this should be shape height because you're doing rows first, but
My question is, if you put row equal to 0 to n rows minus the height, it will still be 0. So if the
okay,
row
just say
or
if I
shape-
set rows to, you have to use the indices I'm using, not yours, because I'm not sure.
If you have the row for the row is like 5 and the shape for
Okay,
the
set
for the
row
shape
equal
is
5.
too, they have the same rows and rows minus rows they're just equal to 0, then your for loop is never executed.
Okay, I'm not so, okay, so if row is 5 for the grid,
Yeah, and the shape, the row for the shape is 5 too.
okay,
And 5 minus 5, you got 0. Your for loop is never executed because I is equal to
okay, I'm doing pseudocode here. I'm not trying to get it exactly.
0.
Okay, I see what you're saying. I'm just trying to do pseudocode. When pseudocode, you're approximate. You're not
Okay.
precise. Okay,
Okay.
so you'd have to. I see what you're saying. You'd have to basically. Actually, I think it is I equals 5. Yeah, I mean, you'd have to do the appropriate translation here, but I'm just trying to be approximate there, okay? I guess what I was trying to do then is show, it sounds like you know how to do this application down here. That's what I was trying to do, but it sounds like you already know how to do that. Okay. But yeah, you have to appropriately map this. And
I thought something's wrong.
no, it's, I guess technically, based on that, I should probably say for, I'd have to sit down and write out the exact, that's why I use pseudocode. When I'm doing pseudocode, I don't want to have to worry about off by 1 errors. I'm just writing out an approximate algorithm, okay? Okay, other questions? Okay, all kind of good with Shapeshifter now. I know it was a tough lab. The big thing about recursion, let me give you a pep talk now. Recursion is tough, okay? And if this lab was hard for you, don't think, wow, I should give up computer science. I'm not cut out for this, okay? That's not true. Recursion is one of the most difficult subjects to grasp, and it will take you some time. So this is definitely one of those cases where the more repetitions you get with recursion, the more comfortable you're going to get with it. And these were some of your first experiences with recursion, so it was going to be difficult. We used to teach recursion in 102 at the end of 102, and it was just too much. That's why it's now presented along with pointers in 140. And we realize that both pointers and recursion are still difficult. So we know that this is going to be one of the lowest scoring labs in the entire semester. Okay? If you're an A student and you ended up with 50 on this lab, this isn't the end of the world. If you're struggling in this course and you got a 10, it's not the end of the world. Okay? This is probably, this and the AVL tree lab are going to be difficult labs. And you may need extra time for it. You may need to see the TAs or me with it. These are going to be more difficult labs. They involve recursion. It is your first brush with it for many of you. It's not going to be easy. Okay? Try not to get discouraged. Try to, appreciate the fact you may not score as high on labs, I believe it's 10 and 11, as you will on some of the earlier labs. That's okay. Okay? As you go through the courses and into 302, you'll see more and more with recursion, and you'll get more comfortable with it. Right? Thank you. Saying wrong would have gotten you booted out right now.
Every lab in 360 uses recursion.
Mm-hmm. So after 302, there is systems programming 360, and almost every lab in there will use recursion. But before you get there, you'll have 302, and 302 will give you more repetition with recursion. I guess the best analogy I can use is in 102, arrays gave a lot of you trouble. But I suspect by now many of you are very comfortable with arrays and vectors, right? So it's the same thing. And functions too. Many of you really struggled with functions probably in 102, but by now functions are probably pretty comfortable for most of you. Well, recursion will be that way for you too eventually. So don't get too bent out of shape if this lab just seemed out of reach for you. This is also why I went over the solution to this, because normally I don't show you the general solution to a lab, but this one I felt it's worth that you see the solution. Also, I want to get across the point that there are patterns. When you're faced with a recursive solution, there are certain patterns you can use. Here, the general form that worked with Sudoku worked here as well. I know it was a little different, but the same idea applied, which is you started at the upper left-hand corner of the grid, and you swept from left to right, top to bottom. And if something failed, you backtracked. Okay? And that's what you did with Sudoku, and that's what you did here. And actually in part one with enumeration, there was kind of the same idea of backtracking, trying the first number and then moving one position to the right. The first one with enumeration was more like just one string, so it was like a one-dimensional grid, but it kind of worked the same way. Start at the first point, then move to the second point, then the third, and always backtrack to the previous element. So that's what recursion, one version of recursion is with backtracking. It's just a systematic search of a search space, or exploration of a search space. Okay? And if it's a grid, you often start in the upper left-hand corner, just sweep left to right, top to bottom. If you have to backtrack, you back up one square, restore the previous state, try the next possible solution. It's just an exhaustive search of the exhaustive exploration of the search space. Okay. So, any other questions? Okay. In that case, we'll move on to AVL trees. If I ever get a cursor. Okay. And let's see, again, I'm going to take a seat. It's been on my feet for a while. Okay, so binary search trees, I kind of introduced them. They're good for maps and for multi-maps. And I said that usually, if they're random, if the data comes in a random order, they're reasonably balanced, okay? Which means that when they're reasonably balanced and you have n items, it typically means that there are log n levels in the BS tree. okay, if the keys are random. Okay, and if the keys are random and there are roughly log n levels, then find, insert, and delete take order log n time, because at each step, each of those three operations goes down one level. Right? Each operation on a binary, each of those three compares the key with the current node, and it goes left or right, but it always goes down one level to the child. So if there's log n levels, you at most do log n comparisons. Okay, so it's fine if the keys are random. But there are pathological cases. Okay, and one pathological case is when the keys come to you ordered. So let's say the keys are A, B, C, D, E. Okay, if we do an insert, what is it going to look like? Let's see. I'm going to Najib? Nazib. So what will the tree look like with A, B, C, D, E?
Every child will go to the right.
That's right. Every child will go to the right. So while it's a tree, it also looks like a big, ugly linked list. And instead of there being log n levels, it turns out that when the data is ordered, or the keys are ordered, the tree will have n levels. That's bad, because now your finds, inserts, and deletes will take order n rather than order log n, because the tree is completely unbalanced. Okay, we call the tree that you're looking at an unbalanced tree. Okay, it is skewed right. That's bad in many applications. Now, sometimes you're willing to roll the dice. You're willing to gamble and hope that the keys are random. There's other times, though, where you're really not willing to gamble, and you need to have the tree be balanced. That is, no matter what, the tree can't have more than order log n levels. Well, people have spent a lot of time looking at how you can rebalance trees. So as you add keys to the trees, how you can rebalance the tree to keep it relatively balanced. And there's all kinds of trees that people have come up with. So some examples are AVL trees. There are splay trees, which we won't cover. There are red-black trees, which I believe you will cover in CS 302. There are B trees. Okay, those are the four most common varieties of trees, of which only AVL trees and B trees will we cover in this course. They all balance trees differently. They all have different performance characteristics. As a matter of fact, splay trees have the best performance in practice, and believe it or not, they're also probably the easiest of the trees, and we used to cover them, but in our new curriculum we don't. AVL trees are probably the next, I don't know whether AVL or red-black trees are actually the next most efficient. B trees are not particularly efficient for what are called in-memory searches, but they're widely used in databases and for storing data on disk, secondary storage. So these are what are called in-memory trees. These are good for in-memory, and this is good for secondary storage, it turns out. But all four trees fundamentally use a rotation in order to balance. All of them use a rotation to rebalance the tree. So at the heart of all of these algorithms is a rotation. I believe AVL trees were the first tree developed for balancing, and appropriately enough, does anyone know what AVL stands for? Pardon?
The first letter.
First letter of the last names, I believe, of the three. I'm not 100%. It's three people developed these trees in collaboration, and each letter stands for one of their names. So it's a good way for you to get enshrine yourself, although it would have been better if they actually, like you have Huffman codes, like Huffman actually got fully recognized. These three, you just know their initials. And here you see me not even, here, let's look it up. Give them their due. AVL trees. There we go. George Atkinson Velsky and even Janil Landis. Wow, there was only two. However, Adelson Velsky had two last names. So there you go. Named after those two. And they were Soviet inventors. 1962. Okay, so they're basically the first to come up with what are called self-balancing binary search trees. So back to, enough with history. So what all these trees have in common is that they keep the number of levels in the tree at roughly log n. It's not exactly log n, but roughly log n. Okay, so how these trees vary is how loose they play with that log n requirement. AVL trees are the strictest. Okay, and then it gets less strict for things like splay trees. So at any rate, we're going to use rotations, and here's conceptually the way a rotation works. You have a tree, so get used to seeing triangles denote subtrees, and B and D are two keys. And what we want to do is perform a rotation. So we're going to change the tree. What we do is rotate B down like that. So B is rotating down so it becomes a left child of D. So if B becomes a left child of D, C becomes a little bit of an orphan, right? Like, gee, C, I loved you, but B's my new left child, so goodbye. So what do we do with C? Okay, we don't want to make C an orphan. C has got valuable information. Okay, so B, by the way, still has A as a subtree. But since we rotated B down, B now has availability. B is like, oh, I gave up D. Didn't exactly give up D for adoption. Actually, D became my parent. Kind of weird. D used to be my child, and now D is my parent, but so be it. At any rate, I no longer have a right child. Well, very conveniently, we can make C be B's right child. Okay? Does that work? Well, let's think about it. In the original tree, we had, this situation where what was C's relationship to D in this tree? What was true about all the keys in C versus D? They were less than. So everything in C was less than D. And what was all the keys relationship? All the keys in C had what relationship with B? They were greater than. Okay? So if we make C be B's right child, we have to make sure that that relationship still holds. So let's verify it. In this tree, we said all keys in C are greater than B. So we made C a right child of B. Is that okay? Yes. And C is in D's left child, so does that mean that, is that okay? Yes. So this is what we call a valid rotation. Okay, we've rotated B down, made it a child of D, and B has adopted D's left child. Okay, and you can do the same rotation, so that's a rotation. We call that a rotation about D, but we can do the same thing. We could go in this direction. We could rotate about B, in which case we get this tree over here. Okay, so that's a rotation. Okay, so you may think, okay, what is it? Let's look at a specific tree now and see how that might, why someone might have thought a rotation might be good. So let's say we just had A, B, and C. Okay, what happens if we do a rotation about B? Based on what I just told you, what's the tree look like if I rotate about B? So A becomes a left child. What is special about that tree on the right that is not special about the tree on the left? It's balanced. So sometimes by applying a rotation, we can make a tree more balanced. Okay? So that's going to be the idea, is that when we do an insertion, we can, by doing a rotation or maybe a couple rotations, we can perhaps keep the tree, get the tree back into balance. And we kind of do this religiously, just like weeding. Okay? It's a lot harder to knock down a big weed than a little weed, right? So same thing, we're not going to let the tree get too much out of balance. Now the way splay trees differ from AVL trees is splay trees let the weed get bigger. Splay trees don't always rebalance. But we're not worried about splay trees, we're worried about AVL trees. And AVL trees are really diligent about rebalancing. Okay? I actually just showed you the simple possible case. Okay? This is what is called a zig-zig case because it goes right-right. Okay? So we call it zig-zig. We could also have this case. Okay, that's also not exactly balanced, but we call that a zigzag case. Okay, this case is no better than this case. They both have level 2. They both have 2 levels, right? And it is, we can't really rotate. Let's say that we tried to rotate this one, so let's get rid of the zigzag. Okay, and let's say we tried to rotate about A. So we got our shiny new toy called rotations. So we're going to rotate, with this case, we're going to try to rotate about B. So B becomes A's parent, and what happens to B's left child? Going to become whose right child? A's right child. Wow, that didn't do us any good. Okay, yeah, we rearranged the tree. It's still unbalanced. So it didn't work so well in the zigzag case. Darn. Let's quit. Nope, let's not. Because if we quit now, we're not getting a nice research paper out of it and we're not getting famous. Okay? So it kind of worked for zigzag. What can we do to make it work for a zigzag case? Well, didn't work to rotate about B that time. Maybe after a sleepless, restless night, you wake up at 5 a.m. and it occurred to you that while rotating about A's child didn't work out too well, what if we rotate about A's grandchild? You think, okay, great. How'd you come up with that? Well, how do you come up with something at 5 a.m. in the morning? The idea pops into your head and you try it. Okay, so we try it. So we're going to do a rotation about C. Okay, so if we do a rotation about C, what's going to happen to B? It's a little more complicated. So if we rotate about B or C, B becomes C's right child. Okay, and C comes up, and it's still a right child of A. So that's something you haven't seen before, but it just, B rotates down and C assumes B's former position. Okay? This doesn't look too good, except does it look like something familiar? Now maybe if we again rotate about C, we will get a balanced tree. And that was the inspiration that those two co-creators had. If they had a zigzag case, then they just needed one rotation about a child. But if they had what is called a zigzag case, they would need to do what is called a double rotation about the grandchild. So the first rotation, I'll do it just to summarize. The first rotation is going to get us to the zigzag case. Whoops. The first rotation will get us to the zigzag case. So that's rotation 1 about C. And the second rotation, also about C, will get us to a balanced tree. So that was their great inspiration. Yes?
I'm confused why on our final tree there, the balanced one, B is to the right of C.
Let's see.
You C is less than B.
Right. So let's use numbers.
Okay, I see.
Let's use numbers.
So the tree was originally,
Let's-
weren't originally saying that C was greater than B.
Right. So there we go. So there's the original tree.
Okay.
And there's, so that's, yeah. Yeah, I see what you're saying. If I'd been doing it, yeah, I see what you're saying. I should have used keys rather than probably to make it a little simpler. Sorry, that would be confusing. So I was just using A, B, and C generically here to mean trees A, B, and C. And the confusion was someone legitimately thought I meant that C was actually the key C, in which case C should never have been to the left of B, right? It should have always been to the right of B. So I was just generically calling them trees A, B, and C. Okay, so that's one thing. The rotations are nice and they're cool, but we still have to talk about balance. Okay, so that wasn't enough for those two authors to get their fame. They also had to come up with a definition for an AVL tree. So it's still going to be, we'll get to the rotation. So there's still going to be a binary search tree. So an AVL tree is a binary search tree. Okay, so it's very important. An AVL tree is a BS tree with additional restrictions. So a binary search tree was limited to at most 2 children. All keys less than you are in your left subtree. All keys greater than you are in your right subtree. Here's 2 more restrictions. Every subtree of an AVL tree is itself an AVL tree. That's important. You can't just have the root obey the AVL property. All of its children must also obey it. And 2, for each node, the difference between the heights of the left and right subtrees is at most 1. Remember, we defined the height of a tree as the length of the longest path. So height, we'll redo it, height equals length of the longest path from a root, or from the root, to a child, to a leaf. Okay, so we're saying that in any AVL tree, the heights of any two children must be within one of each other. And that leads to a pretty balanced situation. Not quite as balanced as you might think, but pretty balanced. Okay? So here are all examples of AVL trees. A single node is an AVL tree. Obviously, these two are. Now, this one, okay, let's start looking at heights. The easiest thing to do is to start, so a leaf is always 0. And an empty tree is considered to have -1. So we say that the height of Binky's two subtrees are 0 and -1. We say an empty subtree has a height of -1. Okay, so what is Binky's height based on this? Because we're just building it up. It's 1. So the height of a node, so another way, height of a node equals maximum of the height of the children plus 1. So that's another way to define the height. It's the maximum of the height of your children plus 1. So the maximum of Binky's two children are 0. 0 plus 1 is 1. In fact, if you look at it, that's right. The length of the maximum path from Binky to any of its children is 1. Okay, so what is the height of Fred? 0. And the height of Eunice? 2. So if we look at any node in this tree and we look at the heights of its two subtrees, there's never a difference of more than 1. Right? Same thing here. If we just do this, 0, -1, 1, 0, 2, 0, -1 over there, 1, 3. You'll notice that if you look at any two children, their heights are never greater than, the difference is never greater than 1. Okay? So those are all examples of AVL trees. Now, here's some that aren't. Okay? Here, Calista is 0, -1. Daisy is 1. This is a -1. Okay? So the problem is, right here, the heights of those two trees differ by more than 1. Right? Okay, this one looks pretty balanced, right? Doesn't look bad, but it's not an AVL tree because if we start doing the computation, by the way, I might well make you do this on exam, 0, 0, 1, 0, 1, 0, what's Binky? 2, what's Fred? 2, and Eunice is 3. However, you can't forget the fact that Fred has an empty left child. And that's where things go south because the difference between height of Fred's left subtree and the height of Fred's right subtree is 2. So you might say, what's the big deal? This still looks pretty balanced. And this was the insight. People that go later always like to tinker, right? You think I can do better. So it turned out when the people who developed splay trees, they took a look at this and said, yeah, I know that doesn't satisfy an AVL tree, but man, you're too picky. That's still pretty balanced. Why do additional work when it's pretty balanced? And so they kind of exploited the fact that we're being too picky here. But back to AVL trees, we're going to be picky, and so we're saying we could do better. We could balance this puppy even better. Okay, so this is not a legitimate AVL tree. So even though some of the, so if you look at the root, it was okay, right? So that's why if we go back here, we didn't say that blah, blah, blah. We didn't say that the root of the tree is an AVL tree. We said every subtree of the tree is an AVL tree. So even though when we come down here, even though the root looks like a legitimate AVL tree, looks very balanced, no difference in the height of its two subtrees, it's no good at Fred. So every node must be a AVL tree. Okay, so I've given you all of the components now. I went through rotations and I showed you how with a zig and a zigzag that I could fix things. And I've told you what an AVL tree is. Let's put it all together. Okay, so let's talk about insertion into an AVL tree. So the first thing is we just shove it into the AVL tree initially as though it were a binary search tree. So we find where it should go in the tree and we put it there. So here's our AVL tree. It's a good one. And I'm going to put a mod in there. Okay, by the way, Dr. Plank does the cases first. I like to do things concretely and then summarize. So I'm kind of going to do it differently. I'm going to show you cases and then summarize. So I'm putting a mod into this tree. So I initially start and do it just like a BS tree. And it goes where baby Daisy is. Okay? So now the heights of the tree may or may not change. Okay, so if we look at it, a mod is a 0. Has the height of baby Daisy changed? Don't just look at it. It's a simple yes or no question. Yes, it's changed. Baby Daisy's height is now 1. That could be a problem. Okay? Because if baby Daisy's height is changed, then she may no longer be a difference of 1 with her subtree, her child, her sibling. Now in this case it was no problemo, right? Baby Daisy's height went to 1. She just became equal with big sister Daisy, who already had height 1. So in fact, at this point, because her height is the same, we can kind of stop. In fact, what we do is we go up to Binky, and when Binky's height doesn't change, we don't go any further. Can anyone tell me why, if Binky's height doesn't change, and we know that baby Daisy and Daisy, they don't differ more than 1, why can I stop at Binky? Why don't I even have to go up to Eunice?
It was valid before, then it changed.
Because it was, Binky's height before was 2, and it was a legitimate AVL tree. So since Binky's height hasn't changed, it can't, and the right subtree didn't change, it can't possibly be that we're violating the AVL tree property anymore. Okay? So we can logically make the deduction that if Eunice used to be a legitimate AVL tree, and Binky's height hasn't changed, and we know the right subtree didn't change, we still must be a valid AVL tree. Yes, Mac?
Can the root violate an AVL tree if it doesn't have a sibling?
Not if it's, no. So we'll run into situations where after an insertion the root could violate it. But it can't violate if it was, if the root previously was a valid AVL tree. Okay, the tree was previously valid. And after an insertion, in the subtree where the insertion occurred, the height of that child didn't change, then it still must be the case that the root is a valid AVL tree. That it can't be invalid. Okay. Let me just get to my last case, okay? Because I want to at least show you one example of rebalancing. Okay. So let's say instead that I insert Waluigi. Okay? That's a problem. Because if I do my renewed height calculations, we get a violation at Fred. Because if we look at Fred's two children, there's a difference in height of 2. Okay? So when we get a violation, we sternly look down at the subtree where the change occurred. And we ask, is it a zigzag change or is it a zigzag change? Just eyeballing it. What does it look like? Zigzag. And what is the rotation supposed to be about? Luther. That's right. So the rotation occurs about the child of the violation. So the violation was at Fred. Therefore, the rotation will be about Luther. So Luther will get promoted, and Fred will rotate down. Okay, so when Fred rotates down, it would become Luther, Fred, and Waluigi. And if you do the calculations at this point, you will find out that it is indeed a valid AVL tree. Okay? And in fact, we will prove that after you've done just one of these rotations, you don't have to do any more looking. So a nice thing about insertions that we will look at next time is that once you have finished doing a rotation in an insertion, either your single or your double rotation, you're done. Okay, and we'll kind of informally prove that fact next time. And next time we'll look at deletions as well. Okay, but you do have enough to get started on your lab tomorrow. You can write the rotations, you can write the zigzags, so you can get started.